Okay, good morning, ladies and gentlemen. This is Professor David J. De Los Reyes. For this morning, I will be presenting my long video format topic, direct current circuit. So I will be discussing uh, DC circuit lesson number 2. Okay, so for those of you who are planning to take up electrical engineering, this is for you guys, or for those people who would like to learn direct current circuit. This is all for you. Okay, let's proceed. My subject matter for this morning will be direct current circuit. This will now be lesson number 2. The last time around, I done or finished lecturing on the introduction of direct current circuit. So at least we now know what is a direct current circuit. Direct current circuit meaning the power source will be a battery and all the loads will be a resistive load. An example of a resistive load is actually lighting, heaters, coffee makers maybe. Okay, those are example of what they call this resistive load. There are no inductors in the so-called load for a recurrent circuit. Okay, let's proceed. The title of the topic for this morning will be, we will be discussing, this is a series connection. Series connection. Series connection meaning the, the loads are actually connected by a line, okay, in such a way that that the current passing through all of them will be the same. For it to be a series connection, the condition is this, the current should be common. Okay? Current is common. So the the marking or the what you call this the marking of a series connection is for it to be considered a series connection, the current passing through all the resistive loads, okay, should be common or the same. Same. For it to fall under the so-called series connection. So if we try to figure out what is a series connection, for the meantime, I brought out a figure here indicating three resistances, only three resistances in series for the meantime. This is R1, R2, and R3. They are all connected in series, and the voltage source is actually this battery, and the terminal voltage will be capital letter B with the subscript T. And this is the plus, and this is the minus. So if we try to analyze a series circuit, this is R1, this is R2, this is R3. The current passing through R1 is designated by I1. The current passing through R2 is designated with capital letter I with the subscript 2, meaning I2. And the current passing through R sub 3, excuse me, will be capital letter I with the subscript 3. And the total current coming from the battery will be capital letter I with the subscript T. Okay? If we try to get our voltmeter here, the voltage across this, sorry for that one, it's B sub 1. The voltage across R sub 2 will be designated as B sub 2. And the voltage across R sub 3 will be B sub 3. So these are the designations of the resistances, currents, and voltages considering a series connection. Okay, let's try to bring out the two most important formulas, okay, under series connection. These are the markings of what we call this series connection. Because by bringing out these two formulas, we could say that the connection should be series. And the first equation for a series connection will be this one. Capital letter R with the subscript T, meaning the total resistance of the entire circuit is actually designated by RT. For it to be a series connection, R sub T should be the sum of R1 plus R2 plus R3, okay, plus I place the last one to be R with the subscript N. Okay? It depends on how many resistances that are connected in parallel. That's why I put a general equation here. The last one will be R sub N. Okay? Or this is supposed to be R total with the subscript N. If there are 4 resistances connected in series, this N here should be 4. So this should be R4. So we do not know what will be the last resistance, so we'll just place this as just simply R sub N. If there are only 3 resistances connected in parallel, of course the last one will be R3. If there are 10, of course the last one will be R sub 10. If there are 5, the last part should be R sub 5. That's why I place it here. The last one should be R sub N. Okay? This is the first formula for it to be considered a series connection, meaning the total resistance is actually the summation of R sub 1, R sub 2, R sub 3, plus R sub N. Okay? And for the current, it will be B total over R total. It's the same whether what you call this series or parallel, but for series, the total current will be the total voltage over R total, and if we try to compute for the total consumption of the total circuit, okay, it will be the square of the current, total current times R total, and the last marking of the series connection is this one. Okay, if you say that this formula here, you can say that the connection is actually a series connection. If I total is the same as I sub 1, the same as I sub 2, the same as I sub 3 for the given figure, we could say that the connection is actually a series connection. Okay? So by seeing these two formulas here, these are actually the properties or the formulas for a series connection. That is, for a series connection, the total resistance of the entire circuit will be the summation of the individual resistances. And for the current passing through all the resistances are actually the same. That's why I place it there. I total should be I sub 1 equal to I sub 2 equal to I sub 3. And this is the so-called common current. Okay? So the distinguishing properties of a series connection is that if you can say that the total resistance is the summation, it is a series connection. And if you can say that the current passing through all the resistances are actually the same, you can say that the connection is still a series connection. Okay? So by knowing this one, even if you cannot see the figure, if they try to give you this equation here, you could say that the connection is a series connection. Okay, property number 1 or characteristic number 1, characteristic number 2. Resistances will be the summation of all the resistances and the current should be common to each individual resistances. Okay, let's try to bring out the derivation. The derivation is just a simple one. Okay, how come we brought out R total for a series connection to be the summation of the resistances? Actually, it emanates from something else, okay? It came from something else. And to bring out this equation here, we shall bring out this whole derivation. For a series connection, the total battery voltage should be equal to the sum of B1 plus B2 plus B3. That's why I place it here. The battery voltage B total is equal to the summation of B sub 1 plus B sub 2 plus B sub 3. Okay? The summation of the individual voltages across the H resistance. And here, we are just talking plus, right? Uh, these voltages here are just real. So, we are just adding it as a real number. That's why I told you on the first lesson that AC circuit is more complicated than DC circuit because in the addition or subtraction or multiplication of currents and voltages, okay, uh, in AC circuit we are using complex numbers, but under DC circuit we are just using the ordinary plus or minus. Okay, meaning to say what we are adding are all real numbers. Okay, they are of the same all real numbers, so we could add them the simple addition, no plus j inserted. Okay, so like what I said, to derive this one, we start with this. B total should be equal to the sum of B1 plus B2 plus B3. B total equal to the sum of B1 plus B2 plus B3. Okay? We call this equation number 1. Okay? But what is voltage under the study of direct current? The product of current and resistance is actually voltage, right? So if we try to apply this formula here to each individual term here, placing the proper subscript, B sub 1 should be the product of I1 R1, and B sub 2 should be the product of I2 R2, and B sub 3 should be the product of I3 R3. We place the proper subscript, okay? It's important. And B total here should be the product of I total R total. So, referring to equation number 1, if we place these values to equation number 1, what will happen? These values here, we put it back to equation number 1. Okay? But there is also a relation which must be needed if we try to substitute values. But the total current, if we try to inspect the figure, I total is equal to I sub 1, equal to I sub 2, equal to I sub 3. Okay? This total current here is the same as this one, I1, the same as I sub 2, the same as I sub 3. That's why, as a next equation, I place it here, I total is equal to I1, equal to I2, equal to I3. So, by using these equations here, plus this relation here, what will happen? The left hand side will be B total, right? It will be the product I total R total. Right hand side will be the product I1 R1 plus I2 R2 plus I3 R3. Okay, we try to simplify now. The operation on the left hand side, the product IR is actually multiplication, right? So we place it in quantity. So when we cancel something, it looks nice. So we could place the left hand side to be the product of ITR total with the quantity. Okay? For the right hand side, we will replace I1 to be equal to RT. We will replace I2 also to be equal to RT. And we will replace I3 also to be equal to RT. So what will happen? Right hand side will be IT R1. Okay? Because we get this relation here. Right? And I2 is still equal to IT. So it will be IT times R2. And I3 is still equal to I total. So this will be I total times R3. Okay? Again, simplifying. The product of I total R total with the quantity. Right? I want to place the quantity because I want to make some cancellations. And this should be equal to, there is a common factor I total, right? Algebra. We factor out, we bring it out. So this is the common factor. What will remain on the next quantity will just be simply the sum. Because I total R1 is this one, right? So it could be simplified to I total common factor times the quantity R1 plus R2 plus R3. Okay? This one here cancels, right? So R total now, this will become 1 and this will become 1. So R total will just be simply R sub 1 plus R sub 2 plus R sub 3 is this. Okay? And in general now, if there are n resistances which are connected in series, okay, we let n to be equal to the number of resistances in series, the total resistance now, if there are n resistances in series, so this is R total with the subscript n equal to, should be equal to R sub 1 plus R sub 2 plus R sub 3 plus R sub n. So this is a very flexible equation here. If there are only two resistances connected in parallel, n will be equal to 2, right? If it is just only one, nothing will happen, right? So if n is equal to 2, if n is equal to 2, there will only be two resistances. If n is equal to 3, there will be three resistances. If n is equal to 4, there will be 4 resistances. So this is a very flexible one. So in general now, for a series connection, the total resistance with the subscript n will be the sum of R1 plus R2 plus R3 plus R sub n. Or this is just simply equal to the summation of the resistances. Okay? For it to be considered a series connection. That's why I brought out the formula number 1, that is R total with the subscript n will be equal to R1 plus R2 plus R3 plus R sub n. Okay? This one here actually emanates from this derivation here, this one. Okay? It is not just that we brought out this equation, but it emanates or it evolves from something else, right? It came from something else. This formula was actually emanates from this equation here. And after simplification, what comes out is R total will be the summation, same as this one. It did not just came out like that. It emanates from a derivation. Okay, that's it, guys. These are the needed concepts for a series connection. So for us to understand the series connection, just think of it that if we try to compute for the total resistance, it will just be simply the summation of the resistances involved, right? And the other markings or properties for it to be a series connection, that is the total current is same as I sub 1 equal to I sub 2 equal to I sub 3, and this is the so-called common current, meaning the current passing through all the resistances are actually the same for it to fall under series connection. Okay, guys. So for those of you who would like to subscribe or watch my channel, you can watch my channel. My channel is at youtube.com/@ProfDavidJ.De If you want to share it, please click share. Good morning from Los Angeles.